Okay, to finally wrap this whole limit um, concept up, we need to talk about continuity. We've already talked about one-sided limits, and that's going to play a role, but continuity. Continuity is not a new topic. We've been talking about continuity since the beginning of limits. We've been talking about continuity in algebra and pre-calc. The idea of continuous is exactly the same um, as what it's been all along, what you would think it would be done outside of math, what continuous means. It means that it's unbroken. It has no holes, no gaps, no jumps. A function that is all one solid piece. So to be continuous at a particular value, there's no interruption, right, in that function at that value. Again, it's unbroken. Okay? There's no holes, no jumps, no gaps. So I think everyone at this point should understand the concept of continuity. So what we want to discuss is how can we show, what do we need to show that a function is continuous at a point? Well, there are three things that you need to do. You need to make sure that your function is defined at that particular value. You need to make sure that your limit exists and that the function value and the limit value equal. So not just one of these things is required. A lot of people think, well, if my function is defined, then it's continuous. Not necessarily true. You might need more than that, and we do. We need all three of these things to hold. If we're trying to determine if we're continuous at a particular location, at a particular x value, where x equals c, the function has to be defined at c, the limit as x approaches c has to exist, and 1 and 2 have to equal each other. I mean, here's a couple of examples that you clearly see are discontinuous. They're discontinuous for different reasons. If you look at the first one, this c value is a discontinuity, is a break, a hole in the graph, simply because the function is not defined at c. There is no y value associated with this x value. When I look at this straight up and down, there's not a single y value that's associated with this x value. This is a hole. There's no other y value anywhere else. So this is a break in the graph because of that. Looking at the next example, c. c is a discontinuity, but not because the function is not defined. When I plug c into the function, I get a y value roughly right about here. So f of c is defined. I have the first one taken care of. The problem is the limit doesn't exist. If I look at approaching c from the left and from the right, the limit from the right would be whatever this y value is. The limit from the left would be whatever this y value is. Those are not the same y value, and therefore the limit does not exist. So while the function is defined, the limit didn't exist. So that one was discontinuous at c. The last one, both of the first two hold. If you look, the function is defined. This function has a y value. There's a point that has this is an x, and there is a corresponding y. There is an f of c. Okay, it's defined. The limit also exists because if I approach c from the left and c from the right, I'm basically going to be approaching this y value right here. So the limit does exist. But the function value and the limiting value are not equal, and therefore causing a break in the graph. Now, if this y value for the c was right here, then this would be all one smooth continuous piece, right? But that would require me to have this to be equal, that the limit and the function equal each other, but they don't. So not just one of these things is required, but all three are required to make sure that your function is continuous at c. When we have a discontinuity, a place where the function is not continuous, we put it into two categories: removable and unremovable, or sometimes called non-removable discontinuities. And whether we have the removable or non-removable discontinuity really depends on whether or not the limit exists. Okay. If you look at this one, this is a removable discontinuity. The function doesn't exist, but the limit from both sides does. This one is a removable discontinuity. The function exists, it's not equal, but the limit does exist. this case, the limit from the left and the limit from the right are two different values, which completely creates a disjoint curve. It's not like we're just making our curve, missing a point, and then continuing on. This is a very severe break in the graph. We're missing this huge gap in between where this piece leaves off and this one picks up. So this one is labeled as non-removable. This one is removable. This one is removable. And really it has to do with the limit. Remember the three things you need for a function to be continuous. This one misses on some of those things, but the big one that this one misses is that the limit doesn't exist. Here the limit exists, here the limit exists, but here the limit as I approach C does not exist. And that's really what makes this a non-removable discontinuity. So to wrap this up, let's look at a couple of functions and discuss the continuity or the discontinuity of these functions. I have the graphs here for each one, but you shouldn't really need the graphs to really look at this and know where the discontinuities are. You're looking at this function. You should know that x can't equal 0, which means the function's not defined there. And if the function's not defined, that alone makes it discontinuous. Noticing that only the denominator is 0, we notice what kind of discontinuity we have. We have a vertical asymptote, which would make it a non-removable discontinuity, because if you look at this limit, it's not going to exist. But knowing all that could then help us with limits in that we recognize we have a vertical asymptote at 0, so if I was trying to do the limit as x was approaching 0 for 1 over x, I would know that the answer is either positive, negative, infinity, or does not exist depending on what's happening. But the continuity plays a role there. This one, I know that x can equal 1. That would make the denominator 0. But it's a different kind of discontinuity in that in this one, it's a removable. Because I got to recognize when x equals 1, the numerator equals 0, the denominator equals 0, and that creates this hole in the graph. Well, the hole in the graph, the limit's still going to exist, but the function does not. And so it's a removable discontinuity. This one is a piecewise function. Now, with a piecewise function, first you look at the pieces, x plus 1. X plus 1 is a line. It's this line right here. And I'm only going to use x's that are less than 0. So the line only happens when x is less than 0. Here's 0, less than 0 is on this side. X squared plus 1 is a parabola. But I'm only going to use x's greater than 0. So that gives me this. Individually, these two pieces, this piece and this piece, are continuous on their own. You should realize that lines and parabolas are continuous everywhere. So if this function is going to be discontinuous, the only place where it could be discontinuous would be where the two pieces meet up. Well, noticing that as x gets closer and closer to 0 for this function from the left-hand side because we're less than 0, this thing's going to get closer and closer to 1. As x gets closer to 0 on this one from the right-hand side, this is going to get closer and closer to 1. And you see right here they meet up at 1. Where the line leaves off, the parabola picks up. And therefore this thing is not discontinuous anywhere. Now if I change this a little bit, let's say I make this a 2. That takes the parabola and moves it to here. So now we don't have this piece. So on its own, this piece here is continuous. On this piece is continuous. But the function overall is going to be discontinuous at 0 because where this one leaves off, this one doesn't. The limit from the left and the limit from the right are different. So when it comes to piecewise functions, not only do you worry about the pieces, but you worry about where the pieces match up as to whether or not you have a discontinuity. Okay? So this run, though, was continuous on the entire real line, because remember, this was a 1 here.